Hey everyone, it's Bradley Bush. Here we have another algebra video. Today we're talking about solving exponential and logarithmic equations. These can be kind of fun if you have the right tools. So that just sounded like a woodworking class plug, but nonetheless it's true. Excuse me, if you have the right tools, these type of equations can be pretty fun. Our to-do list today is we have 3 items. The first item is a quick review, kind of to show you where you generally are in your coursework, your mathematical journey when you start to talk about exponential and logarithmic equations, so you can kind of contrast what you have done before and what you are going to do now to kind of help you understand what's new. The second part of the to-do list is we have 3 tools. And really, these are just rules. In fact, most things we use in math for tools are rules. So we'll give you 3 new rules to help you solve exponential and log equations, and then we'll do 3 examples. So let's start. Here's part of our review, kind of an overview. So in the past, you've probably had polynomial or rational equations given you, and you were asked to solve for x. And oftentimes you had a couple options. You could solve algebraically, or you could solve graphically. So here's an example of a polynomial equation. On the left, x squared plus 3x minus 3 equals 0. It's a polynomial, set equal to 0. You've got an equation, you solve for x. Really, you're just finding the x-intercepts in that equation. That's what it means to solve for x. The rational equation here on the right-hand side of the screen is x plus 2 divided by x minus 3, all equal 4. So you've got a fraction on the left with the top, x minus 2 at the bottom, x minus 3, and that whole fraction is equal to 4. That's a rational equation, and when you solved for x, that would be your answer. And we used algebra often to solve for both of these. And we could also use graphic. We could also graph each of these and solve for x. Something that we'll be doing now is we'll be given, instead of polynomial or rational equations, we're going to be given exponential or logarithmic equations. That means we're going to be given equations that have exponential expressions in them, for example 4 to the x, or we'll be given logarithmic equations like log base 4 of quantity x plus 3. So here are 2 examples of exponential equations and logarithmic equations. The exponential equation is on the left, 4 to the x equals 15, and the logarithmic equation is on the right, log base 4 of quantity x plus 3 equals 2. And we would solve for x in each of those cases. So we need some tools. Now we've kind of seen where we came from, most likely in your mathematical learning when you got to this point, and now how it differs what you did before and what you're doing now. Let's find some tools. Let's arm ourselves with some tools so that we can be effective in solving for x. So here are the 3 rules that we're going to need to use. This would be a great time right now to take a screenshot if you wanted, to save these 3 rules, because really this is the lion's share of what you'll need. Rule number 1. If b to the m equals b to the n, then m and n are equal. So what it's saying is if we have 2 exponentials, the first exponential is b to the m, and the second exponential is b to the n. Notice the b is the same on each of these. The base is the same. So if you've got two exponentials set equal to each other, and their base is the same, because they're equal, you're guaranteed that these two things must be equal. These two things meaning the exponents m and n must be equal. So that's how they come to this conclusion here that m equals n. And by the way, the bases are positive but not equal to 1, and m and n are real numbers. So an example of this type of an equation would be to solve for 2 to the quantity 3x minus 8 all equals 16. And we'll do that example a little bit later. The second rule we have is a rule dealing with logs. And it's really just the definition of log, because we can use the definition of log, meaning the equivalencies, to move back and forth between logarithmic form and exponential form. Logarithmic form being on the left, log base b of m equals c, and exponential form being on the right, b to the c power equals m. We can use those two forms, moving back and forth, to solve logarithmic equations. An example of a logarithmic equation that we could use this tool to solve is log base 4 of x plus 3 all equal 2. And we'll do that example a little bit later. And also, as a side note, in this definition, m and b are positive, meaning greater than 0. B cannot equal 1, and c is a real number. If you're wondering, by the way, what this E-looking thing means, that means is an element of, or belongs to. It's a Greek epsilon. And the fat or bold or strange looking R means all real numbers. So now you know some extra symbols for your math world. The last tool we have, number 3, is kind of similar to rule number 1, but it's a log version. So if log base b of m equals log base b of n, meaning you have two logs, they're set equal to each other, and they both have the same base. They both have base b. Single logs set equal to each other, both have the same base. You're guaranteed that the stuff on the inside is equal, meaning m, which is the input of the left side, has to equal n, which is the input of the right side. So m is the input on the left side, m is the input on the right side. These must be equal. That's where they come to the conclusion here in the rule that if these two logs are set equal to each other, then m and n, the inputs of both logs, must be equal. So we can use that equivalency to solve for x. As we'll see, we'll do this example here below, which is the natural log of quantity x plus 2 minus the natural log of quantity 4x plus 3 equals natural log of quantity 1 over x. And again, the base is positive in this rule. B is positive. B can't equal to 1, and m and n are elements of the positive real numbers. So here's another new symbol for you. R plus means positive real numbers. So R by itself means real numbers, and R plus just means the positive ones. Positive real numbers. That R isn't a really good R, so let me change that for you. There we go. So there are the 3 rules. Let's move on to our first example. So here we go. Here's our example 1. If, and again, here's the rule that we have just to keep our mind present. If b to the m equals b to the n, then m must equal b. So let's keep that in mind. So here's our example. Solve 2 to the quantity 3x minus 8 equals 16. So 2 to the quantity 3x minus 8 equals 16. So at first glance, you look at this and you think, well, they don't have the same base. The thing on the left does, the 2x to the quantity 3, sorry, excuse me, I didn't say that right. 2 to the quantity 3x minus 8, that doesn't have the same base as 16. Does 16 even have a base? Well, this is a really good moment to think about this. Sometimes we have to rewrite the problem to make it fit the rule. That's a very classic tool in mathematics, or a very classic method of approaching a problem. You rewrite the problem so that it fits a rule that you want to use. Rewrite to make fit rule. So how can we rewrite this to make it fit the rule? Well, we have a base 2 on the left side of the equation. How can we change the right side of the equation, the 16, to make it have a base 2? Well, 2 to the 3x minus 8. Can we rewrite 16 as 2 to the something power? 2 to the what gives you 16? Well, let's think about it. 2 times 2 gives you 4. There's another 4, and 4 times 4 is 16, so there are 4 here. There are 4 2's. 1, 2, 3, 4. So it looks like 2 to the 4th power gives us 16, which is true. So perfect. 2 to the 4th power. Now you can see, hey, check that out. We've got 2 exponentials that equal to each other. They both have the same base, which is 2. So what does that mean? Well, according to our rule, that means their exponents must be equal, which is awesome. So we can set them equal to each other. So 3x minus 8 must equal 4. So this is fantastic because now we've got a simple equation to solve. We can add 8 to both sides. That gives us 3x equals 12. We can divide by 3, and the 3's cancel out here. We get what? X equals 12 divided by 3, which is 4. And we have our answer. Here's a little note that is kind of important, so I took time to write it out. So we don't know, oftentimes when we solve for x, we have to check our answer. Sometimes checking our answer is optional and just to see if we made an error in our arithmetic. Sometimes checking the answer is mandatory. It isn't optional. It's actually part of the solution process. And it's kind of hard to know when sometimes. You know, when you're first doing this, it's hard to know when you're supposed to check and when you're, meaning when is it mandatory and when is it just a good idea if you have time. So the times that you'll need to check when it's mandatory is if you have domain restrictions, or, so let me highlight that down here. If you have domain restrictions in your problem, you should probably check because your answer cannot be outside the domain of your problem. So you need to have domain restrictions 1. Or if you have domain restrictions, you need to check your answer to make sure it's in the domain of the problem. The second issue that you need to check is that if you have introduced extraneous solutions because you multiplied both sides of the equation by a variable, you must check the solution to see if it's a real solution, if it's an actual solution, or if it's an extraneous solution. I haven't done either of these two. I don't have either of these two issues in this problem. I don't have domain restrictions because my exponentials have all real numbers as their domain, and I haven't multiplied both sides of the equation by a variable, so I don't have any chance of introducing an extraneous solution. Extraneous solution just means a fake solution that you just created because of your algebra method. So we don't have any of those issues, so we're good to go. We have our answer. That was kind of a long side note, but it's actually super important. All right, let's talk about example 2. This was the example 2 we had. Log base 4 of quantity x plus 3 equals 2. So as we're looking at our equivalency, log base 4 of quantity x plus 3 equals 2, we have a few different parts. We have a b, we have an m, and we have a c. If we want to identify them so that we can then transform them into the exponential version of the log, then we need to figure out what those are. So down here I've identified the b, which is 4. I've identified the m, which is quantity x plus 3, and I've identified the c, which is 2. So now we have those. We can literally just rewrite them in the equivalent exponential form and see where it takes us from there. And my guess is we're just going to be able to write out the answer. So that's going to be nice. All right, so let's see what we have. So b, which is 4, raised to the c power, which is 2, equals m, which is x plus 3. So 4 squared is 16 equals x plus 3. And as we had guessed, this is a really simple equation to solve, right? So subtract 3, and what do we get? We get, x equals 16 minus 3, which is 13. So that was super simple. We also must check x equals 13. Because we have a log, and logs have restricted domains. So, and not only do we have a log, but if we look at our log, the input of the log is where the variable is. So we need to make sure we're not putting something in that would make, after we put the information in, we would make it negative. So let's check. Let's check our problem to see what we have. So our equation, to check our answer, we plug our answer back into the original equation. The original equation was log base 4 of x plus 3 equals 2. And 13 was our x, so we're going to plug that in. Log base 4 of 13 plus 3 equals 2. Log base 4 of 16 equals 2. What is log base 4 of 16, by the way? Is that something that we can compute by hand? Log base 4 of 16, that's really asking us 4 to the what power equals 16, and that power is 2. So that gives us 2. So 2 equals 2. Done. We know that x equals 13 is a valid solution because when we plugged it in, first of all, we didn't get a negative input for a log. We got 16. That was great. The second thing that's important is that when we computed it, we got a valid mathematical statement, meaning 2 does equal 2, which is a valid statement mathematically. So we're good. we know that x equals 13 is a valid answer, and we're good to go. So let's move on to our next example now. Example 3. Here's our last example. This is probably the most complex of the problems that we've done. So let's take a look. We have log of quantity, or ln, natural log of quantity x plus 2 minus the natural log of quantity 4x plus 3 equals the natural log of quantity 1 over x. We're going to use the rule that says if you have two logs that equal to each other, and by the way, log base b can be anything. So in our case, the b, which is the base of the log, is e, which gives us a natural log. So don't let it bother you that in our rule we have a log base b, and in our problem we have an ln, because this rule applies to any of the logs, any base b. So we need to rewrite this problem to fit the rule, because in our problem we have two logs. We have a log minus a log on the left side, and in the rule we have one log on the left side. On the right side we're good, because on the right side we have one log in the problem, and we have one log in the rule, so we're good to go there. But we need to rewrite our left side. And we remember from our rules, our properties of logarithms, that we have, if we have a log minus a log, we can actually condense those to be one single log. So let's actually do that. So if we condense the left-hand side, then we get the natural log of x plus 2 divided by 4x plus 3. And then the right-hand side stays the same. So perfect. Now we have one log on the left, one log on the right. We can set the inputs equal to each other. So that quantity on the left, x plus 2, quantity divided by quantity 4x plus 3, must be equal to 1 over x. We set up the equation and we can solve. So now we're solving the equation x plus 2 divided by 4x plus 3 equals 1 over x. And now we've gone from a logarithmic and exponential equation to a rational equation, which most likely you have seen if you have gotten to logs and exponentials in your mathematical study. So this is great. One way to solve this problem is by multiplying both sides by x. If you multiply both sides by the same quantity, everything stays the same, so that's great. We're doing this because watch what happens. Those two go away. But we also need to multiply both sides by, let's take this and move it down a little bit so I have a little more space. Let's multiply both sides also by 4x plus 3. Because we see that that cancels this side. So in effect, now we have x times x plus 2 equals 4x plus 3. So really I just got a common denominator and multiplied both sides of the equation by the common denominator. And that's a classic way of getting rid of the denominators. in an equation, in a rational equation. By the way, this is also, as a side note, this is also the same thing as cross multiplying, if you want to try that. So if we have x plus 2 divided by 4x plus 3, and this all equals 1 over x. If we cross multiplied, meaning we took 4x plus 3 and multiplied it by 1, and then we took x and we multiplied it by x plus 2, we get exactly the equation that we have on the left. We get the same results we have now. So notice though, before we go, I multiplied both sides of the equation by a variable. So that means my algebraic method may very well introduce a fake solution. In other words, an extraneous solution. So this is one of those situations where it's required for us to check our answers. All right, let's finish solving this equation. So we need to multiply the x through, so we get x squared plus 2x equals 4x plus 3. We need to take the 4x plus 3 to the other side. Minus 4x minus 3, same thing over here, minus 4x minus 3. That gives us x squared. A negative 4x, positive 2x gives us positive 2x. Minus 3 equals 0. Here we just have a polynomial. Polynomials set equals 0. That's an equation that we should have already been able to solve, or we have already solved in our past. So let's do it quickly here. We can factor this as x minus 3 and x plus 1. Then both of these we can set equal to 0. X minus 3 gives us x equals 3. And x plus 1, set that equal to 0. Take the 1 to the other side, and it gives us x equals negative 1. So we've got two options. X equals 3 and x equals negative 1. We need to check both of them. So let's start with checking x equals 3. So again, we're going to check x equals 3. We check by taking the original equation and plugging in the answer we got for x. So we're going to plug in a 3 everywhere there is an x and see what happens. Do we get either a negative in our input, which we can't because we have logs, or do we have an untrue statement coming out mathematically? So let's see. Natural log of 3 plus 2 gives us 5, minus the natural log of 4 times 3, which is 12. So this is 4 times 3 plus 3. 12 plus 3 is 15, equals the natural log of 1 over 3. Well, are these two statements true? Are these equivalent statements? Let's simplify or condense the left-hand side using our log properties. So if you have a log minus a log, we can take the two inputs of the logs and make a quotient. So we can say the ln of the first one divided by the input of the second one equals the ln of 1 over 3. And here we can see, perfect, 5 over 15 is the same thing as 1 over 3. Sweet. we just verified we got a mathematically true statement. So we know that x equals 3 is a valid answer. So now let's check x equals -1. This is our final check. X equals 3 is a valid answer. We're good to go. But now we're going to plug in -1 into our original equation, which is here in red, and see what we get. So the ln of -1 plus 2 minus the natural log of 4 times -1 plus 3, that equals the natural log of 1 over -1. So this gives us natural log of 1 minus natural log of -1 equals the natural log of -1. All right, so we've got an issue right away. We have -1s that are being used as inputs for our logs, and that can't happen. This is a big no-no because logs cannot accept negative inputs. So we've chosen a value which was x equals -1 as our solution, and when we plug it into our log, we get a number that is not in the domain of our function. So what that tells us is x equals -1 is an extraneous solution, meaning it is a fake solution. Let's see if I can write a little bit better. It's a fake solution. It's a solution that we created because of our algebraic process here. So x equals -1 is not a valid answer. So our only answer is the x equals 3. That's it. Thank you guys for watching, and enjoy solving your exponential and logarithmic equations.